Of these events every month, covering in principle all different physics fields in the Quantum Center. So I have actually a list of some of them already. So we'll have, for example, a talk in September by Felix Ringer on particle physics. In October, we'll have Leticia Tarruel, whom, well, you might know, talking on quantum simulation. In November, we'll have Slava Mukhanov talking on quantum cosmology, and so on. So if you have suggestions, please interact with the committee, JJ, Aritz, Jorge, or me, okay? So tell us about your suggestions. They could be here, most of them will be here probably, but they could also be in engineering or even in San Sebastian. Okay? The idea is to cover all the different locations. And basically that's it. So now Aritz will introduce the speaker today. Thank you.
Thank you. Well, for those of you who don't know me, I am Aritz Bernal, and it's a pleasure for me to introduce today Professor Gregory Fiete. It's a collaborator of mine. We do quantum mechanics and materials. Professor Fiete received his PhD from Harvard University. He did a postdoctoral work at Kavli Institute of UC Santa Barbara. He was also a lead Dubridge Prize Fellow in Theoretical Physics in Caltech, and he's a recipient of an NSF Career Award, DARPA Young Faculty Award, a DARPA Director Fellowship, and the Presidential Early Career Award of Scientist and Engineer, and also a Simon Fellowship in Theoretical Physics and a Bessel Research Award from the Alexander Van Humboldt Foundation. He is also an elected fellow of the American Physical Society. So without further delay, he will explain us today a new perspective from atom equilibrium quantum material. Thanks, Greg.
Okay.
The words.
Muchas gracias, Aritz. It's a pleasure to be here. It's my first time in Basque Country. Please feel free to ask questions during the colloquium. I intend this to be more informal. I know that there are different backgrounds here, so I've tried to create a talk which is accessible to those who are not in condensed matter physics. Kind of my main objective is to talk a little bit about some of the areas that I'm working, which is out of equilibrium quantum materials. And to bring us there, I have kind of a review, so I want to say a little bit about what we mean by quantum materials. Is this microphone okay? Okay. And then I'll try to gently ease everyone into some of the research frontier questions in this area of out of equilibrium quantum materials. So of course, as everyone here in the audience knows, that there's a lot of interest in quantum systems, from cosmology and cold atoms to condensed matter to quantum information. And we're kind of in a period of transition within quantum mechanics where we're moving from purely fundamental questions to questions about how we can implement quantum mechanics in various ways, either for a technology like computing or communications, or maybe for some kind of forensics, like detection of things very far away. So, looking at exoplanets that are going around stars that are not our own, we can detect what sort of chemicals are in their atmospheres, what are the temperatures of these planets, et cetera, by looking at molecular spectra. And so quantum mechanics is also involved in the search for life outside our own solar system. So in this talk, I'm going to review what I mean by quantum materials, and then out of equilibrium, for purposes of this talk, the main means by which we'll look at out of equilibrium systems is to have a laser which is shining on a material, and that is going to provide a time-dependent Hamiltonian at a given frequency, so the frequency of the laser. So this is basically going to introduce the idea of a time-dependent quantum system, but with a very specific sense of the time dependence, which is a periodic time dependence at a specific frequency. So that makes the theoretical analysis much simpler when we're in that scenario, and it also corresponds to certain types of experiments that are now being done increasingly more often around the world. So the name for analyzing these sort of systems, it's a Floquet system, which basically means any kind of Hamiltonian or system which is time periodic. And so I'll cover some of the unusual features these flow-K systems, which are generic, they're beyond anything in condensed matter. Any sort of physical system which has a time periodic Hamiltonian is going to have some of the features that I'll describe. And one of the most interesting ones and most unsettling for physicists is that energy is no longer conserved. So in physics, our conservation laws are a consequence of symmetry. So if you have like a translational symmetry, the consequence of that is that you have translational motion or linear momentum, which is conserved. You have a rotational symmetry, that's conservation of angular momentum. And if you have a time translational symmetry, so your Hamiltonian is time independent, then that's a conservation of energy. So if you no longer have time translational symmetry, you no longer have energy conserved. And so that's kind of one of the big crutches that physicists often rest on, energy conservation. So how do we deal with systems where energy is not conserved? It's kind of a very basic question. And then at the end of the talk, I'll give a little bit of sampling of some of the questions that we're looking at in this broader area, so you can see kind of at the frontier of research, what are we exploring and what sort of ideas are out there. Okay, questions at this point? Okay, so quantum materials. So I was on a review panel at a funding agency in the US, and one of the members of the government was asking, okay, what is a quantum material? I mean, isn't all matter quantum at some level? Everything is made up of atoms, and in order to describe an atom, we have to have quantum mechanics. And as you learn in your first course of electricity and magnetism, there's something a little fishy about this kind of planetary model of an electron circling around a proton for the hydrogen atom. See, well, because you learn that accelerating charges radiate energy. So an electron which is going around in circular motion is accelerating, so therefore it's radiating energy. So how can an electron possibly just circle around a proton to form a hydrogen atom? So there's some kind of problem there with that picture, because it would lose energy and eventually spiral into the nucleus. So quantum mechanics, which provides a very different description of matter, allows us to evade that sort of picture, because there's not that kind of classical picture involved, but there's more of a probability distribution of where the electron is. The motions are more complex, and so we don't suffer from that radiation issue. So it's true that quantum mechanics underpins everything, even the stability of matter. But in the context of condensed matter physics and the research ongoing there, quantum materials has kind of a more specific meaning. And so this is phenomena which is often emergent in the system. So it involves many particles, so it's quantum many particle phenomena. And it, in many cases, also depends on the fundamental statistics of the particles, like whether they're fermions or whether they're bosons. So a great place to begin with what is meant by quantum materials to think about superconductivity. So superconductivity is a phase of matter that occurs in a material. As the name suggests, it conducts electricity very, very well because it's not just a conductor, but a superconductor. And in fact, the resistance of such a state is exponentially small, so about as close to zero as you can measure in the laboratory. And what has happened in a state or a material which has undergone a superconducting transition at sufficiently low temperatures is a very quantum phenomena. So the electrons which are moving around in the material are fermions. They have spin 1/2. And these fermions can form a pair. So there's a binding between them, which in many cases is favored by an interaction between the electrons and the lattice of a material. So one difference between quantum physics in a material and quantum physics in the vacuum is that the lattice, the crystalline lattice of the nuclei, plays a very important role in the physics. It changes the symmetry from basically pure rotational and pure translational to often discrete translational and sometimes discrete rotational. That changes the conservation laws. But in addition, there's an interplay with the lattice and the electronic motions. So the lattice can stretch or contract or expand in various directions, and there's a kind of interaction with the lattice that creates an effective, attractive interactions between electrons. Even though they're of light charge, so therefore they would repel one another, within a crystal, there's this electron-lattice interaction, and the excitations of the lattice are known as phonons because they're very similar to photons in many regards. photons or bosons, phonons or bosons. So the interaction of electrons with the phonons, the lattice vibrations of a crystal, creates an effective attractive interaction between these particles of like charge, which would otherwise repel. So they prefer energetically to be bound into pairs. So according to the rules of quantum mechanics, if we take spin 1/2 particles, 2 of them, and we add them, then we either get 0 spin or spin 1 in units of h bar. And so that changes the statistics from fermionic for the individual particles to bosonic for the collection of the pair. And so bosons, we know, like to condense. They like to form a Bose-Einstein condensation. So a superconducting state is a Bose-Einstein condensation of pairs of electrons in a solid. And therefore, you get the sort of properties that you would associate with superfluid. You get some kind of a phase, macroscopic phase coherence over many particles. You can have vortices, like you can have in a superfluid. But because the particles here have an electrical charge, electrons, then it's not a superfluid like helium-4 or low-temperature helium-3, where the helium atoms pair up and then condense. They're electrically neutral in those cases with helium, but here they're charged. So this charge of the pairs of electrons gives rise to interesting responses to magnetic fields. And one of the characteristic properties of the superconductor is that it's a perfect diamagnet. So it would screen magnetic fields up to a certain critical value of magnetic field. So if you apply a magnetic field to a system, then the zero resistance property of a superconductor allows currents to be established very close to the surface of a material, which orient themselves in just the way that those electrical currents create magnetic fields which cancel the magnetic field which is trying to penetrate the system. So it's kind of like a magnetic field version of what you have in electrostatics if you bring a charge near a conductor. That the electric charge of the conductor redistributes on the surface in such a way that it screens out the electric field that's trying to come in from the outside, so you have zero electric field in the conductor. So a superconductor has the analogous feature of magnetic field screening. And the physics of this magnetic field screening in the superconductor is exactly the same as the mechanism for giving mass to matter. So the Higgs boson, which gives matter mass, that mechanism is the same mechanism that describes the decay of a magnetic field into a superconductor. So for condensed matter physicists, it's the Anderson-Higgs mechanism. So this is superconductivity, so hopefully that gives you a sense of why that's a quantum material. It's intrinsically built in fermions, pairing into bosons, and then undergoing a Bose-Einstein condensation. So those are some of the most fundamental of our quantum effects that you learn about in statistical mechanics. And so condensed matter physicists are concerned very much with orders in a system. So what kind of order is there? So superconductivity is a kind of order. It has an order parameter associated with it. So there's some kind of object that we can measure, usually locally. So we can ask at a position in the material, how strong is the superconductivity? And so this is measured by a gap in the single particle excitation spectrum. So how much energy do you have to put into the system in order to create some kind of an excitation? And those properties can be measured with an instrument, for example, such as a scanning tunneling microscope. So I don't have a picture of it here, but there's a microscope which has a tip which is very, very sharp, single atom ideally. And this tip can be brought very close to a surface, and it can move across the surface. If you create a voltage bias between the tip and the surface of a material, then you can tunnel electrons across the vacuum gap, put it into the material, and you can ask how readily do these electrons tunnel as a function of the voltage difference between the tip and the sample, and you can measure the excitation energy locally of a superconductor. So at different points in the superconductor, it might require different amounts of energy in order to tunnel an electron in. So you can measure the order parameter then locally. So that's an introduction to orders and quantum aspects of orders. But condensed matter physicists like to look at all the different possible orders that we might discover. So there could be an order in the charge distribution. So you could have a modulation in the electronic charge distribution in the material, which is different than the modulation of the lattice, for example. So this would be a kind of order that due to electron-electron interactions, the system would like to form a kind of electronic crystal, if you will, which has a symmetry which is different than the underlying lattice. So that's called a charge density wave, and that spontaneously forms at a particular temperature, say. Magnetism is very quantum mechanical. So many of you may have learned in a course in statistical mechanics that, without quantum mechanics, there really isn't a magnetism. It's inherent in the structure of the way that vector potential enters into quantum mechanics, and any kind of magnetic order, be it ferromagnetism, where all of the moments are aligned in the same direction, or anti-ferromagnetism, where moments like to anti-align with their neighbors, or other types of magnetic configurations. So skyrmions is a kind of magnetic texture, where you have, say, in real space, spins which continuously rotate their spins going out from some kind of a central point, and then it will have various properties associated with these skyrmions. There's a charge associated with a skyrmion based on how this magnetic degree of freedom kind of winds in real space. So there are textures in the magnetism as well. So these are examples of phenomena in quantum materials. There are more exotic things that can happen. For example, if you have local magnetic degrees of freedom in a material, which typically comes from partially filled electronic shells, usually of the D or F type shells on the atom. If there's partial filling, then there's something called Hund's rule, which suggests that the moments would like to align for partial filling. And these moments on an atom give a magnetic moment, but the moments between different atoms may not find an order that they prefer. They might not find that they would like to align all in the same direction or anti-aligned or form a skyrmion. They may be frustrated in some way. There might be competing interactions, so that all the way down to zero temperature, these magnetic degrees of freedom, localized in space, actually don't find a preferred orientation. In that case, even at zero temperature, they're fluctuating. And so that's what's known as a quantum spin liquid. So it is a very interesting state of matter for theoretical physicists to investigate. And these quantum spin liquids, in many cases, have very interesting emergent properties. For example, one of the most interesting emergent properties in quantum spin liquids is a lattice version of quantum chromodynamics. So quantum chromodynamics describes subatomic excitations within protons or neutrons, which are called quarks in that case. And they have a confining potential. So if you try to separate quarks in space, then the energy grows proportional to the distance between them. And so if you try to pull them apart, it's like a rubber band. You put more and more energy into the system farther apart they are, which is the opposite of electrical charges, where the farther apart they are, the less they interact. So eventually, with quarks, you pull the energy, you pull them sufficiently far apart that the energy that's there as a form of potential energy allows quark-antiquark pairs to be created, and then you create more out of the vacuum. So there's an analog of that occurs in quantum spin liquids. You can have spin excitations whose energy depends linearly on the distance between them. And so you see an emergent quantum chromodynamics in quantum spin liquids. And there are many interesting properties associated with those sort of fractionalized states of matter, as they're called. So, coming to some of the research that we're doing in the group, there's also this new dimension of topological states, which I'll say a little bit about in this talk. So, topology is a branch of mathematics, which has made a very dramatic entrance into physics, particularly condensed matter physics, over the last nearly 20 years now. And so the example that's often given for topology in the field is to think of a coffee cup and a donut as equivalent shapes from the point of view of deformations. So a coffee cup, you would say, well, there's a space in there where you can put the coffee, and it will hold a liquid. But a donut, there's not a space where you could put a liquid and hold it. However, they each have one hole in them. So you can make a loop with your hands and you can put it through the donut, or you can make a loop with your hands and put it through the handle of the coffee cup. But if the coffee cup was made out of a very flexible material, some kind of latex rubber or something like that, then you could deform one into the other without creating a new hole or without needing to stitch anything together. So in your mind, you might be able to do the deformation between a coffee cup and a donut. And so from the point of view of a topologist, they would say that those are equivalent shapes because they just have the one hole. So if we have quantum systems that don't care about anything except the fact that they have one hole, then that draws a lot of interest from the point of view of applications, because real quantum systems are imperfect. They might have disorder, some impurities in them, maybe their shape isn't exactly what you would like, but if the fundamental aspects of the quantum mechanics don't care about that, then suddenly that particular quantum system becomes very interesting, because it means that there's some kind of quantum mechanics that we can count on independent of imperfections in the system. And so those are topological states of matter. And so there's a large number of them that have now emerged. Initially, there was a quantum Hall system, which is a two-dimensional electron gas subjected to a magnetic field. And if you look at the ratio of the voltage that's developed across the system in a magnetic field due to a Lorentz force that would bend electrons to the current that you're driving in the system, then it turns out this takes a very precise value in the fundamental units of charge and Planck's constant. And that was discovered in the early 80s. But since then, when condensed matter physicists started to impose various symmetries on the system, say we impose time reversal symmetry, or say we impose certain crystalline symmetries on the system, then that allows us with these symmetry constraints to identify new topological states of matter, and there are now a very large number of topological states that have been identified. So this is a very active area of research, one that my group's been heavily involved with. And there's a lot of interesting phenomena to discover within this area of topology. So this interplay of topology and quantum mechanics, again, it requires fundamental aspects of quantum mechanics, and so we put that under the name quantum materials. And then for this talk, what I'm going to focus on is this kind of red highlighted thing here, which is laser stimulated materials. So we're going to take materials out of equilibrium, and the response of the material when it's not in equilibrium, and also the details of how a system relaxes back towards equilibrium is going to reveal a lot of quantum mechanics in the system. So this is kind of my introduction to quantum materials, what we mean, and are there any questions on kind of the space in which we're working here? Okay, great. So now coming to the specific situation of laser stimulated systems. So mathematically, this just means that they're periodically driven. So one of our goals in the field is to try to access some states of matter that we cannot find in equilibrium. Equilibrium imposes a lot of constraints on a system. So if we release that constraint, so we say we don't have to be in equilibrium, we can have some system which is metastable so that it might live for a long time, or it could even be relaxing towards equilibrium and have interesting correlations or orders that it exhibits on its way towards reaching its equilibrium state. That's interesting. So we want to find such hidden phases or hidden states. Phases we should be a little careful with if we're not in equilibrium. Usually phase implies a state of equilibrium, but the nomenclature in the field is sometimes we talk about out of equilibrium phases to mean that they're long-lived relative to some kind of a time scale. But we could be more precise by saying we're looking at hidden states. So these are like hidden correlations in the sense that if you change the system along some axis like temperature or pressure or chemical composition, then you wouldn't be able to achieve these in equilibrium. But you could achieve these kind of correlations or orders out of equilibrium. So that's kind of the holy grail in the field. So it's kind of like taking a material and getting something out of it that you don't think you could get out of it. It's like making it more flexible in terms of its functionality if we want to use that kind of effect later on down the road in some kind of an application. So in a laboratory, when an experimentalist is shining light on a material, there are two limits in which they can work, and these two limits admit different sorts of theoretical approximations that we can use to study the system. So one of these limits is where the laser is pulsed with a very short time compared to the number of oscillations within the pulse. So this short pulse limit, I'll give some examples of what one can find there, but you can think of it as just a little kick to the system, or maybe a large kick as it might be. So it's kind of like you just tapped it really hard, plucked the system, and it tipped it into a system, to a state that it's close by in some kind of a free energy landscape. But once it's there, it might live for a long time. So that's what's meant by metastable regime. So long time is relevant to, relative to the characteristic time scales in the system. So for condensed matter systems, the electronic motion around an atom kind of sets the relevant energy scales and time scales. So electron volts are very typical energy scales. Time scales associated with electron volts are femtoseconds, 10 to the minus 15 seconds. So we're interested in things which are long compared to 10 to the minus 15 seconds for the metastable regime. So in the long pulse limit, where there's many oscillations of the electric field within the pulse itself, then near the center of the pulse in time, then you experience this Fiete limit that I described at the beginning, where the system has a time periodic Hamiltonian over a certain window of time, and then the properties of Fiete systems become relevant to the understanding of the physics of that sort of system. And so in the later part of the talk, I'm going to focus on a regime which is kind of more like this long pulse limit. There's some time periodic Hamiltonian, but one of the challenges is that when you are driving a system for a certain amount of time, the system is going to absorb the energy. So you're going to heat it up. So from the point of view of experimental observations of interesting quantum effects, we want to avoid like the same effect that you would get just by putting the material in the sunlight or something where it's just going to heat up. So we want to see like a coherent quantum response so that the light is ideally like dressing the matter with photons. So we can think of wave functions which are like electrons plus photons, not just hot electrons that have been heated up in some way. So we're looking for non-thermal effects in the physics.
Sorry.
Yes?
It's probably a very, very stupid question, but why, if you're looking for metastable, why do you associate the metastables only with the short pulses? To give you an example, the kicked pendulum, the kicked inverted pendulum, that's actually a case in which you have a Fiete situation in which you are in a metastable. So
no, that's an excellent example. In fact, I could have even mentioned that here. So that would be an example of like a state which would emerge as a kind of hidden phase because it's unstable, but it would only be stabilized by the drive itself. So that is an ideal situation. That's the sort of thing that we would love to achieve in the field. But in practice, what happens is that there are low-lying in energy degrees of freedom that are responsible for the properties in equilibrium, and then there are higher-lying degrees of freedom, which we can often ignore when we look at equilibrium scenarios. But once you drive a system, this kind of stabilization of the inverted pendulum, what the inverted pendulum doesn't have is like higher energy states that you can like couple to. So the challenge that's met in the laboratory is there are higher energy states in the material that then you start to resonantly excite. And then you get a lot of mixing between high energy states and low energy states. So from the experimental point of view, that's kind of coming to the heart of the fundamental challenge. Like, how do we excite a response that we can understand in terms of the low energy degrees of freedom and not worry about the higher energy degrees of freedom? So there's kind of a sweet spot in which one is trying to work. So that's an excellent question. Yeah, but we would love to achieve analogs of the stabilization of the inverted pendulum. That would be great. Other questions? Okay. So to give you a sense of the time scales, I mentioned femtoseconds. So we can think of this as kind of femtosecond. So W here, this is a notation for the inverse bandwidth. So in a solid, there's, due to the periodic structure of the system, there's kind of a minimum and maximum energy that an electron in a given band, as it's called, and I'll introduce that in a moment, can acquire. And so this is a characteristic kinetic energy in the system, ultimately derived from kinetic energies of individual electronic motions around atoms. And so the vertical axis is a kind of distance from equilibrium. It's a little bit imprecise what it's meant by distance, because it depends on the specific system and the way in which it is out of equilibrium. But anyway, this will give you a sense of kind of the degrees of freedom and the various time scales that are typically encountered in a material. So here's a schematic of a laser. So there's kind of typically a Gaussian envelope. There are oscillations within the Gaussian envelope. So this one would be more like the long pulse limit. So there are many, say of order 15 or something, oscillations within this Gaussian envelope. So that's enough so that you're near the center, then it looks kind of Floquet-like. So the blue curve is showing the trajectory of the system. So you shine light on the system, you excite it, so you're farther away from equilibrium, and then over time you relax back. But the electron-electron interactions, these are the effects that dominate the short time behavior typically and describe the early time relaxation towards equilibrium. And then at longer times, the interactions with the electrons in the lattice, the phonons, become relevant. And how far separated these time scales are depends a lot on the properties of the material. Sometimes, in fact, the electron-electron scattering and the electron-phonon scattering are not separated in time. Those energies are very comparable to one another. But this is a very typical situation. And so what I want to highlight here is also this kind of pre-thermalization plateau, which is of interest to those of us working in the field, where the light has passed through the material, but it's not fully relaxed. It's kind of plateaued. So this is like a metastable sort of regime where the system is not thermalized. So you might have the electrons, say, which were excited by the light, with kind of an effective state which is different from the lattice itself, which has not yet absorbed the energy coming from these excited electrons. So when you shine a light on a material, the choice of the frequency you use is very important. So I'll come to this issue, especially near the end of the talk, that you can choose the frequency in order to excite certain properties or certain degrees of freedom in the system selectively. So if you use light which is around the electron volt range, then you'll selectively excite the electrons. And if you use light which is around millielectron volt sort of range, then you'll selectively excite phonons, or maybe magnetic excitations, magnons. So you have selective targeting of your quantum degrees of freedom by how you choose the light. Okay, so let me give some experimental examples now of systems that have been irradiated with light. So this particular material here, tantalum disulfide, and the 1T refers to a particular sort of crystal structure in the system, which is not important for us. The important thing is that this material has a charge order, charge density wave order, so there's some modulation of the electronic charge in space. And so that's shown here and here in kind of image pictures. And what's shown is the resistance versus temperature. This is a very characteristic measurement that condensed matter experimentalists will do. It tells you whether the material is a conductor or an insulator. So what you observe is as you lower the temperature, does the resistance tend to increase, in which case it's an insulator, or decrease, in which case it's a metal, and if it abruptly drops down to 0, that's a superconductor. So this measurement, which just means you take a sample, you just attach 2 leads to it, and you basically measure current voltage characteristics, already tells you a lot about the material. The most important thing is probably, does it conduct electricity well or not? So in this particular system, if you do not shine any light on it, you see as you lower the temperature, then the resistance tends to increase more and more. Notice it's a log scale on the vertical axis. So this is a very good insulator because its resistance is increasing very rapidly as you go down towards zero temperature. However, if you hit it with a single pulse of light, 35 femtoseconds in length, and of a certain intensity, then the resistance abruptly drops from a very resistive state to a metallic state, and simultaneously the charge order changes to a different symmetry type, which is different than something observed at high temperature. So you induce a kind of hidden charge order in the system, and this hidden charge order will persist for some amount of time. And the lower the temperature when it's hit with the light, the longer it will persist. And here's the plot over here showing basically how the resistance recovers, comes out of this metastable state as a function of time. So notice the time scale here is in seconds, if you can see that. And I mentioned that femtoseconds is the characteristic time scale of like electron relaxation, etc. So you can see here, this is like 100 seconds or 200 or 2 minutes. So this is like 17 orders of magnitude longer than the characteristic time scale of femtoseconds. So this is an eternity from the point of view of the electrons. So you have an eternal state, effectively, from the point of view of the quantum motions of the electrons of this low resistance, new hidden charge density wave state, which has been induced by just one pulse of light. Question?
Sorry, I'm very ignorant. I'm sorry I'm pestering you. What's the spatial coherence of the laser beam as compared to the structural transition that you are?
Yeah, so the spot size of the laser that's incident is larger than this region. So it's inducing that order just underneath where the laser is illuminating the system. Now so I don't know how much detail is known about how it propagates, outside of that laser. But yeah, it may be known, but I don't know that. But you can think of this as just occurring like under the spot where the laser is shining. And that's going to be the typical scenario. That you have a material in many cases which is bigger than the spot size of the laser, but you measure the changes at that spot size, or where the laser spot is. And there are various 2 laser probes where you shine a laser which has like a relatively large spot size. You come in with a different measurement which has a smaller spot size, and you can spatially resolve some of the properties. So there was some work that I was involved with in collaboration with experimentalists where they measured like the electron-phonon equilibration as a function of distance from the center of the spot, where you're bringing them out of equilibrium, and then as you go away outside the spot size. And you can kind of see as a function of distance how the electrons and lattice degrees of freedom equilibrate. Yeah, that's a good question. So keep asking. Yeah.
I don't know if I understood correctly. Is the new state found after you turn off the laser, or is the laser all the time?
So it's just a pulse. So it's like you just kind of plucked it. Yeah, you plucked it for 35 femtoseconds, and then you just observe. And what you observe is that this low resistance state and this new charge order in the system lives for up to a few minutes. Yeah. So a few minutes is not long maybe compared to our lifetimes, but again, compared to the electronic motions and equilibration times, that's 17 orders of magnitude difference. So that's really long. Even for like astrophysicists, that's a very long, large separation of scales. Okay, other questions here? Yes?
Relaxation mechanism, the lattice, or what?
Yeah, so that's a great question. So one of the challenges in the field is to understand the details of this relaxation process. So what sets this time scale in particular? So how do we go from like femtoseconds to hundreds of seconds? Like what sort of relaxation mechanism would account for that very long time scale? So how much does it matter that the lattice is relaxing? How about the electronic reconfigurations? How long does that take to go from one kind of a charge order to another? So these are all open questions, which like this sort of experiment really calls to attention. So these are the sort of things that researchers in the field want to understand better. Yes?
So if I understood, and there is a relation between these two graphs, right? But, okay, the normal question would be, okay, what happens at room temperature? I guess you don't have that effect, right? Because
Yeah, so if you're up here at room temperature, then then the resistance here is actually lower than the resistance here. So yeah, so you have to be below a certain temperature to see something interesting happen.
but then, for example, at 200 Kelvin.
Yeah, 200 Kelvin. Yeah, you might see something there. I think that, yeah, I guess the time scales may get short, that it's hard to measure. So in order to measure the resistance, you need a certain amount of time. Like I think the fastest that you can measure resistance is maybe on the order of picoseconds, something like that. So it might be that it's hard to do the resistive measurement in a time-resolved way once you're there, because the time might be too short for that measurement to be done easily. But if you're down here at lower temperatures, then you're in seconds. So this is also like a log plot, as you can see. So, and it only goes up to like 60 Kelvin. So you're probably getting too short to do the measurement in a time-resolved way there.
I guess that regarding potential application, we were trying to push in the direction of having this type of effects closer and closer to the room temperature.
Yeah, exactly. So that's another great point that you make, which is that you know, this example is at such low temperatures it might not be practical for applications. But you know, we proceed with what we have. So if we can understand the low temperature situation, which from the point of view of theoretical modeling is easier in many cases, because you know, our preference as theorists is to work at 0 temperature first, and then later ask what do the finite temperature corrections do. So the analysis is easier here, and also the experimental effect is more dramatic here. But it's true. We would like to push effects like this to room temperature for applications.
68 has some applications already, or is...
Yeah, so I mean here, so I don't know that, so I'm not aware of any engineer who's trying to build something out of this yet. But the field is mainly at the point of exploring, like, what can we find? So, so there's kind of a thrust in the experimental side, which is what is the phenomena that can be observed in the laboratory? And then there's a thrust on the theoretical side, which is how do we create a framework for understanding these experiments, like the question that was asked over here about timescales. Like, how do we create a framework which allows us to predict that in this material, if you achieve a metastable state, then it will probably last a long time, long enough to be interesting for something. So that framework doesn't exist yet. So this is kind of like setting a challenge for people like myself who are working on the theory side to try to address this. How do we predict that?
Thanks.
Sure.
Yeah.
Thanks.
Yes.
The hysteresis-like behavior between 170,
Yeah.
That's in the presence of the pulse or independently of the presence of the pulse?
Yeah, so this is, right, so what's shown here is the blue and the red are with no pulse. So if you go down, say you lower the temperature with no pulse, then you'll follow this blue curve. And then if you heat up again, then you'll come this way and follow the red curve. The green is what you get, you follow the blue, hit it with light, that brings you to the green, and then you return via the green. Yeah. Okay, any other questions? Okay, so when should I stop?
You were the first stop, so...
Okay, anyways, order of magnitude estimate for when I should stop.
1 hour.
Okay, and I began when?
11:40.
Okay, so 20 more minutes or so. Okay. Anyway, I can stop at any point. All right, so as a second example, which is similar in some of the phenomena, but different in details. So this is a very different material. This is lanthanum, calcium, manganese, oxygen. This material is electrically insulating, but it has a magnetic order transition opposed to a charge order transition in the earlier example. So the green curve in this case is what you get as you lower the temperature, and you hit it with a 35-second femtosecond pulse of light, just like before, and then the resistance abruptly drops to a very conducting regime. So you change, in this example, the same sort of thing from the point of view of resistance. You go from insulator to conductor. However, you go from an anti-ferromagnetic order in the insulating state to a ferromagnetic order in the conducting state. And for condensed matter physicists, it's well known that insulators in anti-ferromagnetic order tend to go hand in hand, and conductors in ferromagnetic order tend to go hand in hand. Even if you're not a condensed matter physicist, you know that iron is a metal, it's a conductor, and you know iron is a ferromagnet. So in the old days when you had metallic refrigerators, you could attach magnets to them, although those are becoming less and less common, at least in the US, metallic refrigerators, so it's harder and harder to stick magnets to them, but they're often iron. So, and then this system recovers on a long time scale, which depends on the temperature that you hit it with a pulse of light. The lower the temperature, the longer the time scale. Here, the time scale is actually weeks. So that is a totally different thing than minutes. So in this system, this metastable metallic ferromagnetic state will last for weeks. So I don't know that that's a cutoff. I talked to the experimentalist who did these experiments, and he said, well, you know, I've only left the sample on the shelf for a few weeks and then gone back and checked it to see that its properties haven't changed. So it might actually have a lifetime which is longer than weeks. But from an engineering perspective, that really opens up a door. Because with weeks, you might be able to make a device for some kind of sensing or whatever it might be. Of course, there's still the temperature issue that, you know, it's not room temperature where this occurs, but it's lower temperatures. So you might have to keep it cool, but as long as you keep it cool, then it should be OK. So that's the second example. If you look at other properties, such as how the system absorbs or reflects light, then you see the same sort of properties there. So this is a measurement which can be done on a much faster time scale. So resistive measurements cannot be done so quickly. However, light reflectance or transmission experiments can be done very rapidly. And so they're one of the tools in order to observe very rapid changes in behavior in a system. And so kind of a final example in this category is this strontium titanate. So this is a material which has an order called ferroelectricity. So it's kind of like ferromagnetism. So ferromagnetism is the alignment of magnetic moments. Ferroelectricity is the alignment of charged dipoles. And so this material is only ferroelectric if you apply a strain on the system. So you have to stretch the lattice in some particular way, then it will undergo this ferroelectric transition. However, if you do not strain the system and you pump it with light long enough, and in this case long enough is kind of on the order of 1 to 2 hours, then you can induce this ferroelectric state, which can be observed by an experimental technique called second harmonic generation. So you send in light, and you look at the reflected light or transmitted light, which is at twice the frequency that you sent in. So that's the second harmonic. And this technique is very sensitive to inversion symmetry breaking in the system. So the ferroelectric state breaks the inversion symmetry in the crystal, and then this second harmonic signal picks up the details of that inversion symmetry breaking. So it's a way that you can probe this ferroelectric order. So it takes an hour or two for the system to come into this ferroelectric state. So it's a continuous wave sort of experiment as opposed to the pulse. But then once you have it, then it stays for an hour or two. So it basically stays for as long as it took to get it. So that's also a very interesting effect. OK, so now kind of transitioning into the Floquet systems, the topological states of matter that I mentioned before provide an interesting opportunity to see one of the interesting aspects of a Floquet or time periodic system. So a topological insulator, for those who are not familiar with the material, the experimentally relevant property of it is that the boundary of the system, so you have a finite sample size, the boundary is guaranteed to be metallic by some symmetries in the system and by the topology. So On the inside, the material is an electrical insulator, but on the surface, it's metallic. But it's a metal which is unlike any metal that you can find except on the boundary of a topological insulator. So it has certain properties that we don't need to go into here, but it basically, it resists becoming an insulator, provided that the symmetries are preserved, which in this particular case, it's a time reversal symmetry. So this bismuth-2 selenium-3 is one of the best known topological states. So insulating in the bulk, conducting on the boundary, but in an unusual way. It turns out that its boundary has an energy-momentum relation between the electrons, which is like linearly dispersing. It's called a Dirac cone, named after like the Dirac particles from a relativistic treatment of quantum mechanics. The energy-momentum relation is linear rather than quadratic between energy and momentum. And so this Dirac cone, there's a theorem which says that a two-dimensional system has to have Dirac cones come in pairs. So if it's like a two-dimensional material, if you have one Dirac cone, you must have another Dirac cone at another location in momentum space. However, this topological insulator has this property that you get only one Dirac cone, or in the ideal case, only one Dirac cone, on a surface. So in this material, you get this one Dirac cone on a surface, and so this is one of the ways in which it is different than what you could get in a strictly two-dimensional system. You're not allowed to have one in a 2D system, but if the 2D system is the boundary of a 3D system, then you're allowed to have one. And so this is an idealized sketch. And so here is an experiment which is called angle-resolved photoemission spectroscopy. So it's Einstein's photoelectric effect. You send in light, you eject an electron, and you measure the properties of this electron which have been ejected. So you measure its energy-momentum relation by tracking its trajectory through a magnetic field. And you can reconstruct what was the energy-momentum relation of that electron in the material before it was ejected. So what you can therefore measure is this energy-momentum relation of the electron in the material. So that's what's shown here. You see this kind of like crossing shape. So in this experiment done by a New Geddic's group at MIT, who I collaborate with, he put a pulse of light on the material, which is in the long pulse limit, and he asked in a time-resolved way, what is the energy-momentum relation of the electrons in the solid? And so when the pulse of light is not there, you're supposed to project down in time. So no pulse of light here, no pulse of light here. You see within the experimental resolution this kind of cross shape, which is shown in green here. So that is the Dirac cone, the one Dirac cone on the surface of this topological insulator. However, if you're near the center of the pulse, you see something which looks a lot more messy. But if you analyze it in detail, what you see are Dirac cones which are stacked on top of one another in energy, with an energy shift between them, which is equal to the h bar times the frequency of the pulses with the oscillations within the pulse. Okay? And that's exactly what's predicted by Floquet theory. Okay? So let me come now to Floquet system. So we've reviewed some of the experimental phenomena. So how do we analyze these systems theoretically? So our starting point is a Hamiltonian, which is the kinetic and the potential energy. So T is the time, capital T is the period. So we're imagining that we have a system where any period, or therefore integer multiples of the period, the Hamiltonian returns to itself. We don't need any further details. And once we have this situation, then there's a lot that we can infer about the system. So the first thing is, for anyone who's had a solid state course before, you know that the energy-momentum relation is restricted compared to vacuum. So I mentioned earlier that symmetries are the origin of conservation laws. So in the vacuum, we have perfect translational symmetry. I can move the system by any amount, and the system looks the same. That gives a perfect conservation of linear momentum. In a crystal, I have a discrete translational symmetry. I need to move it by a certain amount in a certain direction. But if I move it by that amount in that direction, then the system looks exactly the same. So I should have something kind of like momentum which is conserved. And what you end up with is a quasi-momentum. So it turns out that as a consequence of this discrete translational symmetry, the momentum is conserved up to some kind of arbitrary factor, which is some integer multiple of 1 over the lattice spacing in real space. So it's called a Brillouin zone, that restricted region of momentum space. So if I have a larger momentum, I can fold it back into this restricted range of momentum. So all the information in momentum space is contained within a restricted region of momentum. So I don't need like all of the momentum. So for a free particle, I have energy is like p squared, at least if it's non-relativistic. And here I only need this restricted region. So because it's periodic in momentum, it also creates a upper and lower bound to the energy of an electron in a solid, because it cannot be periodic if it's unbounded. So there's a maximum energy and there's a minimum energy. So this is the bandwidth in the system. So this sort of effect is one of the most important things that you learn when you discuss quantum mechanics in a periodic lattice. So if you now turn your attention to the energy, this mathematics describes a discrete position symmetry, which gives rise to its conjugate variable, momentum, having this finite window which contains all the information. That mathematics is exactly the same, where now I have a discrete symmetry in time. Then in energy, I have a finite window, which describes all of the states. Okay. So just as in momentum space, this thing can repeat indefinitely periodically, in quasi-energy space, for the time periodic Hamiltonian, the system repeats indefinitely to larger or indefinitely down to lower energy. So there's no minimum energy anymore. There's no maximum energy anymore. And in fact, all the information is contained just in any two states. In this case, it's a two-state system, two-band system, and all the information is there. So because I can shift things around in quasi-energy, I can shift things around in momentum because it's all periodic, there is no longer a sense of high versus low. So I might say over here that this state 1 is lower in energy than state 2. But that's equivalent to a kind of effective gauge choice that I've made. Because equivalently, I could take state 2 and state 1, labeled this way, as my basic states. And that translates up and down just fine. It contains all the information. But now it looks like state 2 is lower in energy than state 1. And so you could say, well, which is correct? It's like, well, they're both correct. It's just an arbitrary choice. But this means I don't have a good notion of energy. I can't say which energy is higher or lower. I don't have a ground state energy anymore. I don't have a maximum energy anymore. And so this then makes the theoretical analysis somewhat complicated. So I can't just minimize the energy of the Hamiltonian and then understand the physics. I have to ask about like how these states are occupied, for example. And typically in a flow-case system, the way that the particles would occupy these is in some non-thermal way. It would not be a Fermi-Dirac distribution, or it not be a Bose distribution for the way that these particles are occupied. It's some kind of a non-thermal distribution, and that's one of the theoretical challenges. How do we, once we found the states of the system, how do we understand how they're occupied by the particles in the system, whatever they may be? Okay, so coming to topology, the details here I don't want to dwell on too much, but it turns out that in equilibrium there's a lot of theoretical work that's been done in what's called the bulk boundary correspondence. So if you know about the interior of a material, and that's where you compute topological properties, theoretically speaking, take the wave functions, you compute some kind of topological invariant, which tells you about the boundary excitations. There is a correspondence between what you calculate for the boundary, for the bulk, and what happens on the boundary. However, when you're in the flow-case systems, this bulk boundary correspondence breaks down. It's much more subtle, and you get effects that cannot occur in equilibrium. So it's another example of out of equilibrium systems possessing behaviors that are not observed in equilibrium. Okay, and as a final experimental example, we can use light to induce topology in a material. So we could take a material that doesn't have any of these topological properties, and we can shine light of the right kind. In this case, it's the very well-known example of graphene, which is a single atomic layer of carbon, forms a honeycomb or hexagonal lattice. It's used for so many things now, has so many interesting properties associated with it. So it's very well studied, very well characterized material. If you shine light on it, which has a circular polarization, so that the electric field is winding around in a circle, say either a right-handed polarization or left-handed polarization, then that circulation in the electric field from the light changes the symmetries of the system in a fundamental way. So graphene by itself doesn't have any magnetic order, so it hasn't broken any time reversal symmetry. Magnetic order breaks time reversal symmetry. But if you impose a circularly polarized light on it, now you have broken time reversal symmetry. You've changed the symmetries of the system, and it turns out that you can change the excitation spectrum, which has this Dirac-like feature in it. There's 2 Dirac cones in graphene. This is just focusing on one of them, but this linear crossing then becomes gapped. And so there's a finite energy to create an excitation in the system, and it turns out that there is a topological edge mode that appears, and you can measure the properties of this edge mode in an electrical transport and see that it follows more or less what is expected from the flow K theory for such a system. Okay. So now I want to come to one of the topics that we've been working on a lot in my group, which is nonlinear phononics. So the examples that I've given up till now have mainly focused on light that is tuned to energies where the electrons are excited. But now we could switch gears and we could ask about light which is tuned towards energies where the phonons are primarily excited. So they're not resonantly coupled to the electrons, especially if the system is insulating, electrically insulating, then there's a gap. And if the light frequency is smaller than the gap in the system, then I don't have enough energy to create any electron excitations. There's only enough energy to excite collective modes like the phonons in the system or maybe magnons. So in nonlinear phononics, what one deals with in a system with inversion symmetry are 2 main types of lattice excitations. So there are so-called infrared active modes. So these couple directly to light. And then there are Raman modes, which couple only at the second order. So they're not directly excited by the light. They have different parities associated with them. So nonlinear phononics, you shine light of low frequency but large intensity. So the low frequency resonantly excites the phonons, and the large intensity creates a large amplitude distortion of the phonons. So when you study phonons in a crystal, if the amplitude is low, then they basically follow a harmonic approximation, and you have a collection of harmonic oscillators. But if you create a large amplitude distortion, then you go beyond the harmonic regime. You have to include nonlinear terms. So you have nonlinear effects, and that turns out to couple the infrared and Raman modes to one another. And so you can therefore excite the Raman modes through this nonlinear coupling to the modes that you directly excite with the light, the IR active modes. And those Raman modes, when they're excited in this way, turn out to have a shift in the equilibrium position about which they oscillate. So there is a transient change in the symmetry of the crystal in this technique. So if you change the symmetry of the crystal, then you can change the sort of electronic properties of that crystal, which depend on the symmetries of the nuclei. So that's the basic idea. And so since I'm about out of time, let me just kind of summarize the sort of things we can do. So there's a material, chromium triiodide, which is known to have a very small energy difference between different magnetic configurations, a antiferromagnetic configuration and a ferromagnetic configuration. So this is a material which has a layered structure. We can just look at 2 layers, which is what's done here. So it's called bilayer. So within a layer, the magnetic moments prefer ferromagnetic ordering. However, between the layers, they could be antiferromagnetic or ferromagnetic. For the bilayer system, the equilibrium preference is to be antiferromagnetic. So various experiments have been done which shows that if you apply a magnetic field which is not too large, around 1 Tesla, you can polarize the system. If you put the system under an electrical gate, apply a voltage, then you can also change the magnetic orientation between the layers. And if you put it under great pressure, then you can change it as well. So the question that we investigated here is whether we can do the same sort of thing with light. So we wanted to ask whether we can create this transient distortion in the lattice via the nonlinear phononics regime that would change the exchange coupling between the layers in the bilayer system. And so since I'm out of time, essentially, I'll just kind of summarize what we did. So it's a 2-step process. So first step is that we do a symmetry analysis of the vibrational modes of the crystal. We write down the allowed terms of the potential between these IR and Raman modes based on symmetry. Then we ask first principles experts, such as Aritz, to calculate the coefficients of these. So what are the frequencies of the IR modes? What are the frequencies of the Raman modes? And what are the coupling constants between the two and the strength of the nonlinear terms? And therefore, we can numerically characterize this for a material-specific case. So the thing that one usually finds is higher energy IR modes coupled to lower energy Raman modes. And the response of the Raman mode is greater if its energy is lower. So we want to choose the laser frequency to target the IR modes, and then we end up exciting certain Raman modes. And the net effect that we find is that certain Raman modes respond with an amplitude. This is an amplitude of the shift in the equilibrium position, much more than others. So we can ask, well, this mode, this Raman mode, changes the symmetry of the crystal in which way? And then calculate how the interlayer magnetic constants change. And we indeed can find a sign change. So we can change the material from antiferromagnetic to ferromagnetic with the light. And so this is a reversible process. It can be done more or less instantaneously. And so it gives great control over the material. And then we looked at another material which, in addition to a magnetic transition, also has a topological band transition. And we found that that topological band transition goes hand in hand with the magnetic transition. OK, so with this, I'd like to thank my collaborators, one of whom you all know very well, and maybe another. You may know Maya as well. But these are various students and postdocs and affiliates with the group, not Arthur, but the others who we've been very grateful to have collaborated with on a number of these theoretical projects. So thanks so much for your attention. I'll just leave this summary there.
Thank you very much, Greg. We have time for short questions. Maybe you want to use the microphone so it can be recorded on the talk. I should have used it also. Is there any other question?
Yeah.
How relevant is the bilayer structure in order for this IR Raman modes to be
It's
coupled?
not at all relevant.
Okay.
So we looked at the bilayer system mainly for ease of theoretical analysis, because it meant that the number of atoms that we needed to consider for the effects was smaller, so it made the computations easier. But there are experiments on 3-dimensional systems as well. So one of the interesting effects that I didn't cover here is that it looks like you can use the nonlinear phononic effects to make superconducting-like effects at room temperature. So we don't have a room temperature superconductor, but you can take a high temperature superconductor and pump the right sort of phonon mode, and then you can measure the optical response of that superconductor. And for a short time after you've pumped that phonon, you have the optical response of the superconductor indicating that it is a superconductor, just as if it were an equilibrium superconductor at room temperature. So from the point of view of like optical response, then it has superconducting-like features. Although there's a lot of debate in the community about whether that's a true superconducting state, because you can't measure a Meissner effect, for example. So you can't measure the screening of a magnetic field. And there might be other effects that are going on that might mimic that optical response of a superconductor. But that's a three-dimensional system. So yeah, so there's nothing here from the point of view of the basic physics of it that restrict it to 2D.
So essentially, you didn't trust the ab initio guys.
Well, no, I think that interests, 3D interests them too. It's a question of what they can compute.
Any other question?
So you basically want to find in the experimental examples that you did, you want to find new state, new phases, right?
Yes.
And for that, you shine the object or the material with some laser. But since this is some phase that exists there, couldn't you just bring the material to that state by just cooling the system from a high temperature?
Well, so in the examples that I gave, you can't reach those states by cooling. So it's not a property of the low temperature state. But it's something which is, like the equilibrium parameter, is not accessible. So in the first example that I gave with the charge density wave, you can achieve that same charge density wave state that you observe with the pulse of light if you put the material under strain. So if you can replace, in that case, the laser pulse with the strain on the lattice. And in the second example, with the ferromagnetic metallic state, you cannot get the ferromagnetic state with those conditions under which you hit it with a light. But if you apply a magnetic field, then you can induce a ferromagnetic conducting state. So in those two examples, there's an equilibrium route that you could use to get those orders in a different part of parameter space. So they're not yet at the holy grail level where you have a state that under no equilibrium conditions could you get it. And the ferroelectric case also, if you strain it, you could get the ferroelectric. So those are all examples where in the equilibrium parameter space, you cannot get that charge order, you cannot get that magnetic order, you cannot get the ferroelectric order. So for equilibrium conditions, the light gives you access to something which is hidden.
I don't mean that you reach the equilibrium, but that by cooling you reach a metastable state that lasts much longer than any other problem, any other effect in this.
Yes.
So you cannot do this by just cooling.
No, I mean you won't get that state at all just by cooling. Yeah. So if you just cool those systems down under the pressures and the temperatures in which the experiment were done, and external fields, if you cool them down to arbitrary low temperatures, you will not get that charge ordered state for the tantalum sulfide. You will not get that metallic ferromagnet for that lanthanum calcium manganese oxide, or the ferroelectric state for strontium titanate. So cooling alone won't do it. You've got to have the light. Unless you go off in a different direction, like you apply strain or you apply another field, like electric or magnetic field. Yeah. Yes?
Does the laser pulse have to be finely tuned to the system, and how many photons are contained in one of the in the pulse?
Right. So the frequency of the pulse, so the frequency is important within some range. And I think the different systems that I showed, like how fine-tuned the frequency is, vary somewhat. I don't remember those numbers offhand. The intensity is very important. Like in many of these, you have to have a critical intensity of the laser. So if the intensity is not high enough, even though your frequency is correct, then you won't induce those new states. So it's like you have to pluck it, but you pluck it at the right spot, so to speak, like in a guitar string analogy. But you've got to create a large enough amplitude. You've got to pluck it hard enough at that spot. So the intensity really matters. In terms of how many photons are there, I have a vague recollection that I once did kind of a back of the envelope calculation, and it's I think it's on the order of a photon per electron in some, in a two-dimensional sort of counting way. I could be wrong, but that's my vague recollection. Yeah.
Maybe one other question. Have people thought about using other states of light, for example, a fog state that is in the same Gaussian mode?
Yeah, that's a very interesting question. So I think one of the frontiers in the field is like kind of pulse shaping generally. So how do you want to organize the photons in a very general sense that are hitting the material? So I think it's related to your question, but even more broadly, people are asking about that. So in the field of quantum chemistry, there's a lot of pulse shaping in order to create different reaction rates in systems. So for chemists, shaping the light and doing interesting things with it has been a tool for a while. But condensed matter physicists, I think, are only really starting to think in that direction. And there's a lot of new light sources, so which are becoming available. I guess one thing that I didn't emphasize here before, but it's a general theme that in the same way that we have a lot more data available on lots of systems, so Aditya and I were discussing like biological systems earlier, there's just a lot more data available, so there's more theoretical analyses that can be done in principle because there's more data that you can use to constrain it. Like on the experimental side, there are much more widely available laser sources. So there's much more frequency range that's covered. They're more cheap than they used to be. They're more stable than they used to be. And like the time resolution is getting to be better. So it used to be certain frequencies you could not resolve time. You couldn't do a time resolved experiment. But like all of this space is kind of filling in. The frequency is filling in, like the time resolution is filling in. So I think that there's an exciting frontier here in general, like using laser sources to take materials or anything out of equilibrium, whatever it might be, and coming up with creative ways to ask, like, how do we bring it out of equilibrium? How should we apply the laser to the system in order to get some kind of interesting response? So to me, it's kind of just like it's just a new dimension to like quantum mechanics, this non-equilibrium way using a laser to create interesting quantum effects. Yeah.
Maybe I can rephrase the question by saying, okay, you are treating the laser classically, is that correct?
Yes.
You treat it as a semi-classical field. You are not considering the field as a quantum field.
Yes.
For you, it's just a classical field. Right?
Yes. Yeah. I mean, right.
So far.
Yeah. So
we'll see in the future.
Yeah. That's true. And that's a very good approximation, I think, for the systems here. I think. Now I understand what you're saying about Fock states. So I think about like small photon numbers, for example. I think that in general, that's interesting. I mean, certainly there's interest in few photon detection in many cases. So you want to know like what kind of a quantum system is very responsive to small numbers of photons, even going down to like 1 photon limit. So I mean, my familiarity with that is that in condensed matter physics, I don't know of effects like in the sort of sample sizes that people look at that would be sensitive to a coherent response to few photons. I mean, mainly it's like heating. Like if single photon detectors are basically based on superconductors at their superconducting transition, so that 1 photon that's absorbed heats it up and then raises the system above the superconducting transition, you get a rapid change in resistance. So like few photon detection is like based basically like on a kind of a classical effect of heating, rather than like a quantum response of the superconductor to the photon. So I don't think that, I think if we have a good candidate, like if you have a good quantum system in mind where like small numbers of photons would produce an interesting effect, then I think that probably that would get a lot of attention. But I don't know anything offhand other than this kind of like heating example.
Are there any other questions? Maybe we're a little bit run out of time. We thank the speaker again.
Okay, thank you.